jump cube. Jump times jump times jump. All right. So what I would do is I would just write it out 3 times. Like that. And I'm going to FOIL out the second and third one, and then distribute the first one to it. To me, that's always the easiest way to write out cube stuff. So we get 4x squared plus 6xy, 6xy, so that becomes 12xy, and then 9y squared. And then I'm just going to distribute that guy into it. When I distribute that guy in, we're going to get 8x cubed, 24x squared y, 18y squared, excuse me, xy squared, plus 12x squared y, 36xy squared, 27y cubed. And then just start combining the stuff. Excuse me. We get 8x cubed went first. Look for any other x squareds. There's 2 of them. Bless you. X squared y, xy squared here and here. What is that? 42, I believe. No, 50. 54. Math is hard. So 54 xy squared and a 27y cubed. Today we will talk about how you factor or sums and differences of cubes. So there will be some, we'll see a couple extra special patterns here and there as we go through. Does that help on 61 for you guys? Really, honestly, whenever you see don't to any power, just write it out that many times. If it's to the 4th, do 2 and 2, and then just distribute it. Bless you. There's really no shortcut that's worth remembering. It's the amount of time it takes you to try to remember the shortcut. It's just as easy. Just okay. All right. Make sure your name's on that, and we'll start 6-4 today. Yeah, why not? It's good for us. Every once in a while, I feel like. So Jackson, the stuff like I was saying, it was just distributing property and add stuff. It's pretty quick as you get into it. I ran out of flavors on your Saturday. I appreciate you tearing this off. Thank you. Mighty nice. That's mighty nice. Fine, I'll stop talking. Can I help you? I know, you're messing. Why are you throwing stuff? Seriously, children. So, last night, or I'm sorry, not last night. Yesterday, one of the things that we had started to discuss was the idea of I was looking at pacing and looking at some stuff, and I realized that we don't have 3 full chapters, so we only have 2 full chapters to roll through. So we can actually spend our time and do polynomials right. And I was able to save ourselves a couple of days here. When I was looking at the final that I had written, I looked at the 2016 fall final, not the 2017 fall final. So we'll be all right. So it's not a big deal. So what I'm going to do with the way that it's worked, it actually works out rather nicely. Between today and tomorrow, we'll talk a little about factoring, solving polynomial equations. In this section, they talk about just using real solutions. Bless you. But I'm going to spend time to talk about real and imaginary, because we all know that imaginary solutions are a thing. So we're going to talk a little bit about both of them, so we're able to spend a little bit more time on that. As well as then on Friday on the half day, in section 6.5, we start doing division. And there's two forms of division. One of them is long division, which, you know, goes a long way through, but with polynomials. It's procedural, but it's perfect for a half day. And then we come back on Monday, we can finish the rest of the division stuff, which is synthetic stuff. So depending upon how far we get through that, I would go for the first 5 sections, and then quiz on that. The earliest would be Tuesday. More than likely, it might be Wednesday. Then obviously we have that the next week, and we have that half day on Thursday, so we can I can split up a little bit of section 6.6, and it works out rather well when I was pacing things through last night. Oh, what do you got, Mike? No. I'm sorry. I'm sorry. If you're friends, I apologize. We can, you know, it happens. It was a joke. He's not even paying attention, I know. So, factoring, you guys have all factored. You guys have factored before. You guys all know how to factor. You guys have done many different styles of factoring. For example, if I look at either of these two, these are very similar to things that we've done in the past. The first one says 4x squared minus 24x. If I was to, well, first of all, is this a factor or a solve problem? Why is it factor? Perfect. Everybody see that? So the difference between factor and solve is that solve always has an equal sign. This one doesn't have one, which means we just have to factor. So what is the very first rule of factoring? Always. GCF, or should it be FCG for you today? Backwards. Holy shit, look at that aspect on that mother function. Yeah, anyway. Wow, that one just really sunk quickly. I thought that was good.
I mean, I got that. I didn't say that. I didn't say that in laugh.
You just made a new enemy.
I'll get over it. Anyway, so first rule of factoring obviously is GCF. What's the GCF of 4x squared and 24x? 4x. So if you factor out the 4x, you're left with x minus 6. We okay with that? Now, hypothetically, if this said equals 0, what would your two zeros be? 0 and 6. Good. If this equals 0, you can't just divide out by, you cannot move the 24 and divide by x. That does not work. That eliminates zeros. That is a very, very bad thing. The other one, we have 2x squared. I'll write this down here so we have a little bit more space. Was 2x squared plus 11x minus 21. And this is a trinomial one. Now, again, first rule is always to search to see if there's a GCF. In this case, there is not. So what was the rule that we were always working with our trinomials about factoring? Remember? Yeah. That's scary. Well, yeah, exactly. Multiply your tails, of course, sir. Multiply your tails to see what adds to the middle. So if I multiply the tails here, I get 2 times negative 21, which is negative 42. What times what is negative 42, but it adds together to get positive 11. Well, let's list them out and see what we can find. 1 and 42. Whew. 2 and 21. Do you guys remember the trick for checking to see if 3 goes into something? Exactly. I don't know if you heard what she said, guys. Add the two numbers together. What's 4 plus 2? Is that divisible? Divisible by 3? Yeah. So it would be 3 times 14. Hey, look, it's a happy pie day. No, I see you're like, oh, yes, it's for circles, yes. So when we do this, we did a split middle term. the 14x has to be the positive value. Reason why it has to be the positive value is because the middle term is positive, so you have to go with the larger of the two. Now you can do one of two things here. I wrote it down as plus 14x minus 3x. Can I also write it as minus 3x plus 14x? Yes, and I probably should have done that because it's easier to factor. Remember, this is the style we do by grouping. If I put the negative first, it's just less of a headache later on. Because automatically it's going to make my terms, my two things that go in parentheses, negative. I don't have to worry about the distributive property of the negative here. Okay? You can do it either way. It doesn't matter. It's just, I just realized that when I wrote it, I should have the other way. So now I go through the process of grouping, which we'll do a bunch of again today. What's the GCF? X. What's the GCF? 7. Is it a positive or a negative 7? Positive 7. Now I remember from when we did this stuff earlier this year, a lot of times you guys forget to put the sign for that secondary term. Make sure you're either put a plus or minus there. So here's plus 7. So the question then becomes, are the things in the parentheses the same? Yeah. So we take those out. And what's left? And there you go. That's factor by grouping. Just a little reminder of how things work. Just a little reminder of how this works. What would change if this equaled 0? Hey, you just find the zeros. And you can probably look at that right now besides our phones. Gentlemen, no way. You can survive an hour without it. I know you can do it. If we set those equal to 0, you get 2 zeros, you get 3 halves and negative 7. What are your tails doing for this one? Something good. Up, up. They're up, up. It's positive, even. But so now what happens when you get to stuff like this? Dun, dun, dun. Can't. There's no equal sign. Now, I like where you're going with that. If you had x plus 3, x plus 3, x plus 3, then you wind up with a whole lot of middle terms, wouldn't you? See where I'm going with that? So you can't do that. So here's what happens. There are special patterns for what are called sums and difference of cubes. Just like we did with difference of squares. If it was first term perfect square, second term perfect square, why, good morning. Thank you, sir. If we did first term perfect square, second term perfect square, if it was subtraction, we knew it was 2x or x minus 2x plus things like that. Here, it's different. Here, you wind up with, I'm going to use this. When you have sum and differences of cubes, we have sums and differences of cubes. For our example we just had, we had x cubed plus 27. Now, perfect cubes, it's going to be relatively simple to figure out. More often than not, it's going to be stuff that goes up to maybe 5, 6 at the most. Okay? You always have a calculator for most of this stuff, whether it's the smart calculator or a regular calculator. You just take a cube root out, and you'll be able to figure out whether or not something is a perfect cube. The perfect cube root of 27 is. So what I want to do is show you what happens with these patterns. This is the same thing as x cubed plus 3 cubed. You all right with that? So the pattern then becomes, first it's x, excuse me, x plus 3, x squared minus 3x plus 9. The way that this works, guys, is you take the cube root of the first and the last term, and then it's just squared, multiplied together, squared. Notice the signs. Same, change, same. Plus, minus, plus. What happens when it is a minus you get minus plus plus. So the first term is always the same as what it was. The second term is always the opposite. And the third term is always positive. Same, opposite, plus. That's how these patterns always work. Same, opposite, plus. Those will always be the sign patterns. Yes. When I snapped the picture, it was just a little vertical thing for that. Yeah, no. Sometimes it does. It's just getting grab it cleanly. So if I have something like this one where, let's say it was x cubed, make it really easy, minus 8. What's the cube root of 8? 2. Cube root of 8 is 2, so this is the same thing as saying x cubed minus 2 cubed. So it would just be x minus 2, x squared, plus 2x, plus 4. Also, the other thing that happens here is if these were equal to 0, you're only going to get one real solution. The other are, I'm sorry, you'll get one clean solution. The other ones are, you'd have to use quadratic formula. Forgot what math class I was in for a second there. All right, you'll use the quadratic formula to solve it. That trinomial part there will not be factored. It won't be factored. So that's what these things look like. So going back to that example, well, we just did the x cubed plus 27. Well, sometimes just like the one we had up here, if I go back, sometimes it's just ugly. Sometimes it's 16x to the 5th minus 250x squared. And you have to factor that. But guess what your first thing to do is always? Find the GCF. The variable GCF is pretty simple. It's what? There's an x squared or u squared. I'm always going to go back and try to rewrite as x squared. It's just how my brain thinks. I know that I can factor out an x squared, so I'll have an x cubed, and it'll be minus something. But then I have to think, well, 16 and 250. I know they're both even. You're right there. Take out a 2. Watch what happens if you just take out a 2. You get 8 and a 125. What's the cube root of 8? 2. What's the cube root of 125? 5. That's how you get the pattern here. And now, when you have a leading term coefficient here, is when you have to pay close attention. So as we factor this, we still have this 2x squared. Inside the parentheses, this is the same thing as saying 2x quantity cubed minus 5 cubed. Because if I cube 2x, I get 8x to the 4th. That's where that comes from. Okay. Now I follow the special pattern. The special pattern says a minus b, a squared plus ab plus b squared. Well, my a value is 2x. My b value is 5. I put it all together. I get 2x squared, 2x minus 5. What's the quantity 2x squared? Basically, what's 2x times 2x? 4x squared. What's 5 times 2x? 10x. And you're done. Anytime you have coefficients with sums and differences of cubes, that's where you guys will make a simple mistake. Okay? You'll forget the cube or square, the coefficient, but you won't forget the variable. So my suggestion is always rewrite it like I did here with like the quantity 2x squared, If there was a 5, put it in parentheses if you have to, and then write out the pattern. You write out the pattern a couple of times, you'll remember it. You'll be like, okay. So there's your sums and differences. That was the first one that was new today. But then, remember yesterday we talked briefly about this. Let me just redo this one. Yesterday we talked briefly about what do you do to factor that. Now we haven't done any, there are no special pattern stuff, there's nothing like that when it comes down to factoring cubes with this, just if it's 4 terms. But anytime you see 4 terms, always try to group. Always, always, always. That's the dead giveaway of the thing you can do. Okay? If there's no GCF, go right to group. So if you group this, group them how they sit. So remember we group them here. What was the GCF? X squared. Then I'm left with x minus 2. Again, the reason why I put that negative inside the parentheses is to remind myself to take it out. So what is the GCF of a 9 and an 18? Take out the negative 9. Because I want what's in the parentheses to look like what we already have. Are the things in parentheses the same thing? Yep. So we write it down. And then you're left with x squared minus 9. And then you say, oh, wait a second. Isn't that a difference of squares? So it means to factor it fully, I have to rewrite it as? Yep, x plus 3 and x minus 3. For fun, what are your tails doing here? Down, up, right? They're down, up. Where are your zeros? 2, -3, and 3. Good. How many changes of direction can this have? 2. 4 terms. So you have nth degree has n plus 1 terms, n minus 1 possible. Or sorry, it has n plus 1 possible terms, n minus 1 possible changes of direction, and n total zeros, whether they are real or imaginary. All right. Well, what changes if I throw one in with an equal sign? What's that? You're just gonna solve it. Yeah. Set it equal to 0. So take a second. Find, solve that one out. Do the factoring. Solve it. See what we get. Is that when did it start? That was what, 2 Saturdays ago?
Oh, yeah, it was on Saturday.
Yeah, I'll yeah.
Yeah, that was, it got in my eye multiple times.
That's lovely. Yeah, that's right, because it was 2 Saturdays ago. Because then the following day I took my motorcycle into that for storage. So I remember it being like 40 degrees out. Yes, sir. Oh, good. Sounds smart. I'll pull it up in the calendar. I'll figure that out. Hopefully this wasn't terrible. You had a 3 3x cubed, 7x squared, minus 12x, minus 28 is 0. No GCF. That would be bad. Start factoring via groupings. We have 3x plus 7. Take out the, excuse me, negative 4. So then you have x minus 2, x plus 2, 3x plus 7. Gives you 2, negative 2, negative 7 thirds. And for fun, tails are doing what? Down, up, you mean? Reading from left to right? First term is positive, exponent is off. So I say down up because I'm reading it from left to right. Okay. Try that 81x to the 4th minus 16. Let's see what you can think of here. It's a 4th degree. It's a 4th degree. But here's the trick. Is the first term a perfect square? Yeah. It is, because how do you get x to the 4th? Isn't x to the 4th x squared squared? Right. So x to the 4th is just x squared squared, isn't it? So x to the 4th is a perfect square. Is 16 a perfect square?
Yes.
Is 81 a perfect square? All right, so is that a subtraction symbol? Yes. So this is a difference of squares. The difference is 9x squared minus 4 and 9x squared plus 4. I don't know, is it? No, you're right. I see where you guys are going. What's the next step? I gotta do that again. For which one? Not both. The left one only. Is 9x squared a perfect square? Is 4 a perfect square? Is that a subtraction symbol? Did you answer yes to all 3? Okay, so you get, 3x squared minus 2. Oh, sorry, x squared, sorry. 3x minus 2, 3x plus 2. And I do it again. Is 9x squared a perfect square? Is 4 a perfect square? Is that a subtraction symbol? Did you answer yes to all 3 questions? And you leave it. Wait, why? Why do you? Because that's how you get a difference of squares. Because if you have a plus minus, then your middle term goes away. Here, that will give you an imaginary root. That'll give you imaginary roots. Okay. Now, look at the next one. 4x to the 6th minus 20x to the 4th plus 24x squared. Oh, factoring, here's so much fun. So 4x to the 6th minus 20x to the 4th plus 24x squared. Your first rule of factoring is always to do what? GCF. What's my GCF here, guys? 4x squared, very good. So if I factor out a 4x squared, I'm left with x to the 4th minus 5x squared plus 6. You okay with that? Okay. Now that's a trinomial, isn't it? Look at your exponents. It goes 4 to nothing. All right. Starts with a 4, it's cut in half to the middle term, and then it's cut in half again, so it's an exponent of 1. Anytime you have exponents that go down, 4, 2, 1, 6, 3, 1, 8, 4, 1, as they're getting cut in half or they're getting cut down like that, You can factor it like you would anything else. What times what is 6? You add together to get -5. -2, -3. I can factor it the same way. So actually, you know what? Let me do this real quick so we have a little bit more space. So when I get to this point here, I still have my 4x squared. I have x squared minus 3, x squared minus 2. I can still factor that trinomial, even though that it has the higher degrees, excuse me. It's okay. There's nothing wrong with it. Because if you FOIL that out, you're still going to get x to the 4th minus 2x squared minus 3x squared plus 6. It still works. Okay. Now, is x squared a perfect square? Is 3 a perfect square? Can't do anything else. Is x squared a perfect square? Is 2 a perfect square? And then I am done. There's nothing I can do here anymore because the 3 and the 2 are not perfect squares. Even though it's differences, I would be done. Now, how many total zeros should I have here? 6. Very good. I can have 6 total zeros. Now, do you guys agree that I'd have zeros at plus or minus square root 3, plus or minus square root 2? Now, x squared can be rewritten as what times what? X times x. So if I did that, if I have 4x times x, what are those two zeros going to be? 0 and 0, which accounts for how many total zeros do I have? 6. 0, 0, plus root 3 minus root 3 plus root 2 minus root 2. I have 6 possible zeros. Now, one of those zeros is repeated. Which 0 is repeated? 0. So when a 0 is repeated, all right, let me rephrase this. It doesn't have to be the number 0 being repeated. It could be 8. It could be 7. It could be -4. It could be the square root of 3. It doesn't matter. Whenever you have a 0 that's repeated, we say that it has multiplicity. It's called multiplicity. Okay? If the number of times it's repeated is even, it changes direction at that 0. And you guys know that. You guys know that from when you factored that, x squared plus 6x plus 9, you got x plus 3, x plus 3. If you graphed that, it had a 0 at -3, and it touched the equation once. That's where that comes from. It's called multiplicity. So if I'm going to look at the graph of that one, what are my tails doing for 4x to the 6th? Up, up, they're up, up. I have zeros at 0, square root of 2, negative, square root of -3, square root of 2, and square root of 3. You guys okay with that? If it's up, up, that means it has to go through here, change. It should look like that. Throw that in your calculator. Yes, ma'am. It changes direction at that value. It doesn't have to be 0, it could have been 7. That's what I mean by if you ever have any zeros that are repeated, it's said to have multiplicity. It just means it changes direction at that 0 if it's even, or it goes through it if there's 3 or 5 of them. Yes, sir. Yes, it changes direction at wherever there's multiplicity. If the multiplicity is even, it changes direction there. If the multiplicity, if it's odd, it goes through it. We're just getting there. All I'm doing here, guys, is just so I'm planting the idea of what is going to happen in a week or so. So every little bit of me just saying, hey, what is this term? What does this mean? What do the zeros represent? What are your tails in? What is the graph going to look like? By just doing a little bit of it here and there, as we start to do more of it, you guys will be more comfortable with it. It's not that your homework tonight you'll have to do any of this. It's just me getting you prepared so that when I start talking about it, you're not going, "Ah!" or like, holy shit, look at that. You're not doing that to it, okay? That's the idea. Okay. Yeah, I think that's it. Don't worry, I'll give you some props here. Yes, ma'am. Oh, no, don't worry about it. Well, do you have a question? No, I'm just gonna run out of time. Let's do those for today. Tomorrow we'll do all the solving stuff, and I'll show you a couple of tricks on the calculator as far as the how you can do some of the solving with the weird word problems. Again, it's not like it's any more difficult than the quadratic ones. Yeah, Mel? Like 33, 6, 36, 39, go by threes. That's what that means. Does that make sense, guys? Every third just means go by threes. Well, hopefully you can count by three. We'll do that. PDF is already up. You should be able to go. Oh, what fun.